Let's work through this circle problem carefully and keep track of every relationship, because there is a very nice connection between the two chords and the diameter. We have a circle with center O, and PR is the diameter of the circle. A chord QS crosses this diameter at point T, and QS is perpendicular to PR at T. The two right triangles are PTQ and STR. We are told that the hypotenuse PQ is 4 units, while the other hypotenuse SR is 7 units. And our goal is to find the radius of the circle. Before we begin, if you enjoy these step-by-step geometry problems, make sure to like the video, subscribe to the channel, and leave a comment with your answer before we reach the final result. Now, because PR passes directly through the center O, PR is the diameter. We know that the diameter is twice the radius, so PR equals 2 times R, where R represents the radius. Next, notice something important about chord QS. The diameter PR is perpendicular to chord QS at T, and a perpendicular from the center of a circle to a chord bisects that chord. Since O lies on PR, the line PR passes through the center and is perpendicular to QS. Therefore, T is the midpoint of QS, which means QT equals TS. Let's give these two equal pieces a name. We will call each of them A. So, QT equals A, and TS also equals A. Now let's name the two pieces of the diameter. Let PT be B, and let TR be C. Since P, T, and R lie on the same diameter, the complete diameter PR is simply the sum of PT and TR. Therefore, PR equals B plus C. So far, everything is expressed in terms of A, B, and C. Now let's look carefully at the next geometric relationship. We can obtain the required relationships directly and rigorously using the intersecting chords theorem. This theorem says that when two chords of a circle intersect inside the circle, the product of the two pieces of one chord equals the product of the two pieces of the other chord. Here, the diameter PR and the chord QS intersect at T. Therefore, PT multiplied by TR equals QT multiplied by TS. In our notation, that gives B multiplied by C equals A multiplied by A. In other words, B times C equals A squared. This relationship is going to be extremely useful. Now let's also use the Pythagorean theorem in each of our two right triangles. Remember, the Pythagorean theorem says that in a right triangle, the square of the hypotenuse equals the sum of the squares of the two legs. For triangle PTQ, the hypotenuse PQ is 4 units. One leg is PT, which is B, and the other leg is QT, which is A. Therefore, B squared plus A squared equals 4 squared. Since 4 squared is 16, we have B squared plus A squared equals 16. For the other right triangle, STR, the hypotenuse SR is 7 units. One leg is TR, which is C, and the other leg is TS, which is A. Therefore, C squared plus A squared equals 7 squared. 7 squared is 49, so C squared plus A squared equals 49. Now pay attention because we can combine these equations with the intersecting chords relationship. We already know that A squared equals B times C. So, in the first equation, instead of A squared, we can use B times C. That gives B squared plus B times C equals 16. We can factor B from both terms, giving B multiplied by the quantity B plus C equals 16. Now do the same thing with the second triangle. Since a squared equals b times c, the equation c squared plus a squared equals 49 becomes c squared, plus b times c equals 49. Factor c from both terms, and we get c multiplied by the quantity. B plus c equals 49. Now we have two very useful equations. The first is b multiplied by b plus c equals 16, and the second is c multiplied by b plus c equals 49. Notice that both equations contain the same factor, b plus c. That is exactly what we want, because b plus c is the entire diameter. If we divide the second equation by the first equation, the common factor, b plus c, cancels. So we get c divided by b equals 49 divided by 16. Therefore, c is 49 16ths times b. Instead of immediately introducing a complicated fraction, let's make the relationship easier to handle by saying b equals 16k and c equals 49k, where k is some positive constant. This works because their ratio is 16 to 49. Now remember that a squared equals b times c. Substituting b equals 16k and c equals 49k, we get a squared equals 16k multiplied by 49k. 16 times 49 is 784, so a squared equals 784k squared. Taking the positive square root, because the length must be positive, a equals 28k. Now, let's use the Pythagorean equation from the smaller triangle. We had a squared plus b squared equals 16. Substitute a equals 28k and b equals 16k. So we get 28k whole squared plus 16k whole squared equals 16. 28 squared is 784, and 16 squared is 256. Therefore, we have 784k squared plus 256k squared equals 16. Adding those coefficients gives 1040k squared equals 16. Now divide both sides by 1040. We get k squared equals 16 divided by 1040. Simplifying that fraction by dividing numerator and denominator by 16 gives k squared equals 1 divided by 65. Taking the positive square root gives k equals 1 divided by the square root of 65. Now we can determine all three segments if we want them. Since b equals 16k, b equals 16 divided by the square root of 65. Since c equals 49k, c equals 49 divided by the square root of 65. And since a equals 28k, a equals 28 divided by the square root of 65. But our main target is the diameter, so let's move directly to that. The diameter PR equals b plus c. Substitute the values we just found. PR equals 16 divided by the square root of 65 plus 49 divided by the square root of 65. Because the denominators are the same, we simply add the numerators. 16 plus 49 is 65. Therefore, PR equals 65 divided by the square root of 65. Now notice the simplification. 65 divided by the square root of 65 is simply the square root of 65. So the diameter PR is square root of 65 units. This is approximately 8.06 units. Since the radius is half the diameter, we now divide square root of 65 by 2. Therefore, the radius r equals square root of 65 divided by 2 units. Numerically, that is approximately 4.03 units. And there is a beautiful shortcut that confirms this result. Look at the two given chord lengths, 4 and 7. Their squares are 4 squared, which is 16, and 7 squared, which is 49. Add them together and we get 16 plus 49, which equals 65. Therefore, the square of the diameter is 65, meaning the diameter itself is square root of 65. Once again, the radius is half of that. So the radius is square root of 65 divided by 2, which is approximately 4.03 units.